So thank you for coming. My name is Namhyung Kim. This talk I'm going to talk about the uftrace updates with focus on the dynamic tracing. So this is a brief introduction of the uftrace is a function graph tracer for user space. It's heavily inspired from the kernel ftrace project, and it traces single process execution. For those not familiar with it, I suggest visiting the project homepage. We have some GIF animation to get the idea of the project. So there's a build update. There are a couple of sorry. No. But I updated my slide. It's compatible to my animation stuff. Yeah. That's it. So, but there's a simple build updates. There are a couple of external library dependencies, but now it can build without any of it. So let's call the optional dependencies, but with reduced functionality. And there's automatic arguments updates. Basically, uftrace supports argument recoding, but it requires users to specify all the arguments, number of arguments, what type was it, and now it can trace mathematical arguments recode. There are two forms of automatic arguments. One is for external functions. There are a selected set of relevant functions, so we hard-coded the list of functions and the argument types. And another is for the internal functions you write in your program. So it parses the dwarf debug information and extract the argument information from that. So by using dwarf arguments, so you need to use the dwarf handling library from Pendant. And for now, it only supports the primitive data types like integer or strings. But it also provides some human readable outputs like try to symbolize function addresses, and also enum constants are symbolized, including bit masks. But there's a problem in string handling that it's basically a pointer, so you need to follow the reference, the pointer values, but it can result in a seg fault when the value is not intended as a pointer or it has a broken values. So current approach is to prevent like that, is to build a list of allowed mappings by reading proc file system and allow pointer access only in the white list of the allowed mappings. That should be some race conditions, so it's not 100% guaranteed, but it works well for in practice. So this is the example of automatic arguments. The A option is to enable all functions to automatic arguments. This is traced to the PWD function binary to print current working directory. So you can see all the string arguments and the values. And the green one, in third line, is the enum constant for local values, categories. And in the last line, you can see the blue arguments. That's it. It converts the pointer value to a simple strings. Okay. Next is perf event integration. uftrace uses perf event in two ways. One is to get system information like task management or task creation or task exit or task scheduling information from kernel. The other is to get the hardware performance counter values. Usually it doesn't require root privileges, but unfortunately many systems, many distributions now disallow perf event for normal users, so you might need to change the settings in the file system to having values more than 2 to enable it for normal user account. So basically the task information is enabled by default, but you need to use a read trigger to read performance count values for your function, for your program. So it works for the arbitrary function you choose, and it reads values at the beginning and end of the function and shows the difference during the function, so you can see the values and metrics related in your function execution. And there are 3 types of events are supported for now, and all of them are general hardware counter events like CPU cycles or cache reference or branch instruction, and it's like that. So this is the example of reading perf counters. The T option is to specify trigger options, and I chose foo as a function, target function, and then it follows by a read and PMU cycle command line. So when it enters to the foo function, it first reads the PMU counters, and then right before it exits from the function, it again reads the same PMU counters and shows the difference between beginning and end of the function, and shows the count values only for during the functions. And it also calculates the metrics, in this case IPC, for that functions. So you can use this feature for any of the function you want. And there's a TUI updates is for user interface stuff and for terminal user interface. by using mCourse library. And basic idea is to reduce the duplicated analysis for different analysis comment. And by using TOI, you can run report, graph, and info kind of analysis in a single run. But it does not include replay type of analysis for now, but it's planned to add it later. Also, I'm thinking of changing the filter settings dynamically so that you can focus on functions you're interested by changing the filters in TOI. This is the example screenshot of TOI. You can move on the lines of your interested functions, and there are some keys to help to developers navigate to functions significant to your analysis. Yeah. Let's move on to dynamic tracing. Basically, dynamic tracing is to enable tracings for functions only you want. The basic operation is similar to how kernel ftrace dynamic tracing works. Then, basically, compiler needs to add the no operation in the instructions in the each function in the prologue of each function you want to trace. But basically, it's ignored since it's only no operations. But after that, you can enable functions you want to trace by specifying them in the command line. So you can turn on the tracing only for those functions. It works good. It's nice. But there are some problems there, since it's basically require a compiler to add some instrumentation code and make it no operation. And so it basically needs recompile your application. Well, it's basically a requirement of the uftrace, but there are many requests that wants to avoid that compilation process for use of uftrace. So it'd be nice if we can skip that procedure. And also, if we allow compiler to recompile for your dynamic tracing, but there are limitations that some settings like position independent code does not work well with the changing to no operation for the mcount prologue functions. Like usually we can use mcount option for GCC to make it to call to mcount function as a no instruction, but it doesn't work for me for the position independent code. So in that case, you cannot use dynamic tracing. So there's an update for that. I call it the full dynamic tracing. The full dynamic tracing doesn't require compiler support, and it can trace normal binaries not compiled with PG or similar options. It only needs symbol table in the binary, and it since worked on x86 as an experimental project. But the basic idea is it's very similar to how kernel K-proof jump optimization works. So basically, it parses the instructions in the function prologue, and if it's traceable, it can save the original instructions in prologue to a different location, and then overwrite the instructions with a jump to mcount or similar to uftrace functions. So this is an diagram to explain it. If there's some function like this, for dynamic tracing, it analyzes first few instructions in the program to be compatible with the dynamic tracing. And if it is, in this case, first 3 instructions are copied to a different location. And it also adds an instruction to jump to the original location after that instructions to be called later. And it also replaces those instructions to call to the entry function of the uftrace functions through trampoline instructions. And when this function is called, first the dynamic, and it will move to the dynamic entry function, and it does all the things that need to be done in the uftrace, and then it will try to find the original instructions and then move it to the original instruction, and then finally move to the position after the call instruction in the original function. So we can trace this full function with the dynamic tracing like this. So it needs instruction parsing in the program. So I use for now the very simple approach to support dynamic tracing. At this stage, it only cares the PC relative addressing. Since the copied instruction will be executed at a different location, will have different PC value, so no more PC relative addressing won't work in this case. So we reject that kind of function to be applied for dynamic tracing. And to check the PC relative addressing, it just check the operands of each instruction, and it has some form of branch or jump instructions with some offset. It's usually add to the PC, or it references memory address by using base address of the PC register. So in that case, they are rejected during the instruction parsing phase. And it also needs to detect whether there are jump into the prolong instruction in the middle of the function. And if there's a jump instruction to the other function and it's not in the first of that function, it usually does not happen in the code generated by compiler, but some handwritten assembly can have that kind of jumps. So we reject those functions too. And to be safe, it also rejects indirect jumps, since we cannot guarantee which address it can have. So try to apply this technique to many kind of binaries. This is an example to do it with uftrace itself. But you have the general idea that the success rate is, it has total more than 700 functions, but only 74% of the functions passed successfully, and 24% were rejected due to they have PC relative instructions in there or other jump instructions. So maybe we can increase the success rate by by supporting piece-relative addressing by replacing, modifying the instructions in the copied instructions to have the right value for the PC. But still, it needs to deal with all the instruction details and I guess many of trial error or some very corner cases. So I also think about another approach that is kind of reverse patch, like unpatch, or it let the compiler generates all the original instrumentation code and leave there itself. Leave the call to encount functions. And then it patches functions not interested at runtime as a null. So it has same effect. It will have same effect, but it can apply to all kind of functions since compiler already add the instrumentation code there. So this approach also in the review now in Workflow x86. And I also added the size filter to the dynamic tracing. The basic problem of uftrace is it generates too much data, too many data, so it generates event record for every function execution. So there are so many entries for its execution, but we cannot know which is important or not. So we somehow need to reduce the amount of trace data. But one of the factors you can decide that is using the function size of the function. So it basically assumes that the function has a small size. Function is not that important. It may be true or not, but anyway, you can apply size filter to filter out small functions and only trace the function has large bodies. And I'd like to mention of some problem I encountered during the dynamic tracing development. There are, in terms of register saving across function calls, there are two types of registers. One is colo-saved registers. It's usually for scratch registers and registers for the argument passing. And these registers, the contents of these registers are changing if after you call another function in your function. And colo-saved registers are registered to have same value after you call another function. So uftrace usually don't care about the colo-saved registers, only colo-saved registers need to save and restore the original values. And they are scratch registers, and it assumes that callers doesn't assume it have same values after function call. So it also don't care about the scratch registers and only care about the registers for the argument passing. But it has a problem that GCC has an option of IPA-RA options that uses scratch registers. It assumes that scratch register has same value after function calls, but it can be applied only if it can see the definition of the function it calls and verify there are no instructions override that register during the function execution. So if compiler knows these registers are not changed, then by calling this function, it just keeps the original value of the register before function call and use that register after the function call. So that breaks the assumption of uftrace. So it resulted in crash or abnormal behavior after applying dynamic traces. So solution to that is to save all the call saved registers for dynamic tracing. And there are also some problems about return address handling. Well, it's not only for dynamic tracing, but it's a problem of uftrace in general. But anyway, it needs to deal with return addresses. So since uftrace wants to trace function returns as well, it needs to know when this function, current function, returns. But usually compiler only adds the instrumentation code at the beginning of the function. Well, there's an option to add both, but it has another kind of problem there. So we usually use the PG type of compiler instrumentation. To do that, uftrace change the return address saved in the stack to be hooked the return address to be called by uftrace before return to the real function return location. But the problem is that some applications assume that condition of there's some assumption of the return address, but if uftrace change that return address, it breaks the assumption and the application breaks or do some undefined behavior. And there are some system libraries called inside, not explicitly, but there are some cases it unwind frames not shown in the application, like C++ exception or backtrace or non-occurable to situations. uftrace needs to happen that situation and to restore original return address before doing that. So there's needs to be a way to deal with. As I said, compiler also provides options to add instrumentation both for entry and exit of functions. The GCC has F instrument functions. Clang has X-ray instrument options that they can add instrumentation both for beginning and end of the function function. Or you can use recover trigger by uftrace. So by using T options, you can specify a function, and then to return the original address during the function execution. So if you know exact function that caused trouble regarding the return address handling, you can use this recover trigger to work around the problem. But it's hard to know which function generates that kind of problem. So I added auto recover feature that it recovers all the parent's function return addresses when entering the child. This only thing we want to know is function return of the current function. So when we know when the current function exits, we can set up the similar the return address hooking for the parent function. So it's if there's the nested function call, like foo calls bar or bar calls bus, we only know to when the bus function is returned. And at the return of bus function, we also need to also can change the return address of bar function, so that after that we can know when the parent function returns. The basic idea of this auto recover is to have original return address in the stack as much as possible. Before that, uftrace changed all the return addresses in the stack. So, like I said, other system library took a look at the stack to get the return address. It will see invalid values, but by applying auto recover, you can see the original return addresses of all the parent functions. So it still have single function, current function of return address was changed, but all others have the original return address. So it reduced the possibility of the problem of return address. But it still had some cases still have the problem dealing with return address, so I need to improve this kind of support to make it more robust to dealing with return addresses. So this is it. Any question?
Talking about return addresses, so how do you plan to handle tail call optimization? So that's the case where you have a function. At the very end of that function, you call another function, and the compiler can decide to optimize that call into a jump to the other function instead.
Yes. In that case, tail call optimization, it can handle that case as well, since after the final jump, it can also enter to the next entry of the next function. It also hooks return address, but the return address already hooked by the original function. So, but it changed, like the next return address will point the original return address, not original return address, but it will point to the return address of uftrace. So after returning the second function, it will move back to the uftrace and then to the original function. So it will see two returns for uftrace, so it can be traced.
So in one of your earlier slides, you had basically function arguments for strace, so you can decode like RB arguments. So strace is another program which decodes those. I mean, as a user, you want to know if you're in a type of program what the arguments are. This question for you as your implementation, but also maybe for the room with LTTNG. That's very useful to the user, but I've seen when tracing LTTNG events, it doesn't do that, it only has the pointer. Could you have some insight into, it seems like you just implemented that in uftrace, how that was done, and if we could do that also in LTTNG if we don't have it today?
Sorry, I didn't follow the question. Please.
So one of your earlier slides, you had syscall support, and you actually decoded, without knowing the references, what the arguments to, let's say, exec VE was, for example. And you get the same functionality in strace. As far as I'm aware, that doesn't exist in LTT.
Library calls. That's
Yes.
not system calls. This is calling libc. So it's not the syscall that's instrumental. So it's really at the user space level in this case.
Is there any way to get that?
The syscalls?
Yes.
Yeah, the LTTNG, kernel tracer traces even the strings and everything for syscalls.
Okay, maybe it's another argument or something, another option.
Yeah, but it's a different tracer. I mean, this is tracing user space.
Yes.
Yeah.
Yes.
So to question, you compare this with the S-trace, right?
Yes.
So S-trace basically use ptrace option to every syscall you need to go into the kernel and then move back to user space, but it's only using user space. So you read the value of the register to pass on the function call, and you can know the pointer value of each function, and then it dereference the pointer and get the string values, not going to the kernel. So that's the difference.
Yeah, so it should be more efficient and faster.
Yes.
In the case of S-trace against the kernel, I'm sure there's a cost for doing that as well. I would love to get that in. You say it's there already,
There.
which is awesome. Great to hear.
So with ptrace, it's actually 2 round trips to the kernel and scheduling that you need to do. For S-trace, it is really slow. LTTNG does it directly on site, and it writes to the ring buffer right away when you take the syscall at the kernel level. It's much faster, but this is really user space only. Yeah. So if you just do the syscall from user space bypassing all libraries, you won't see it.
Okay, yeah, we should talk offline, because I've only seen actual just instructions, not the actual decoded arguments. Thank you.
Hey, Namhyung, amazing work. Thanks for continuing the work on uftrace. So one of the things that you were mentioning was dynamic tracing. It's super interesting that you're trying it out, and I've banged my head on this before. I saw that you have with libcapstone 75% coverage at least. Did you try some other tracers like Pendant, which provide an API itself to find out the function boundaries? And some of these tools, which not just Pendant but like any other dynamic tools, which the security folks use, they're much robust in finding out function boundaries. So have you tried some other libraries?
Actually, I investigated some possibilities, but I want to use, when I chose the dependency of external library, I focused on the availability of on various architecture and distributions.
Oh, yeah, yeah.
So I want to not only for x86, and I also care the ARM or other architectures too. So, and the capstone is available for many distros. So I chose
Yeah,
that.
yeah, that is. Apart from that, what about methods which or functions which are probably like inlined, or they don't have, you don't see the prologue in the methods themselves because they have been inlined and they're part of and some other methods, and because of the compiler optimizations, like then you cannot trace them at all.
Inline functions?
Yeah.
Yeah, we don't have way to trace inline functions yet.
Okay. And I think the final limitation would also be on symbols, which is very generic.
Yeah, I'm thinking of, to improve that. But now, it needs book table and binary.
Okay. Amazing work. Thank you.
Thank you.
Thank you for the presentation. I have actually 2 questions. The first is related to the trigger for the recovery. Yeah. So when the trigger is triggered and you replace the return address, it means that that function won't be traced.
I mean, it changes return address, all the parents functions. The parents functions are already recorded, so you cannot lose the entry of the parent functions. the only thing it cares is the return timing of the parent functions. But when it used recover trigger, at the time it changes the parent address to original values and executes function bodies, but it leaves the return address of the current function. So it can detect the return timing of the current function, and when it sees the current function exit, it then restores the hooked value of return address of parent functions.
Yeah. And the second question is, well, actually, it's an answer to Sushaka. It's like I have a fork on my GitHub that is using fast GP or dnist to be able to answer dynamic tracing, and it could be used for inline functions. If you know the address of that function, you can insert a dnist trace point in it safely. And but you just need to know the inline address of that inline function, which I think it could be done probably with the help of the compiler.
So you mentioned issues reading the strings that associated with pointers. Did you consider registering your own segmentation fault handler and basically kind of taking care of those segmentation faults yourself when you're generating it?
Yeah, I will think about that. Thank you.
Thanks.
We're going for the break. Thank you very much. Thank you.